I'm going to move on to the prediction of fatigue failure next. And in this case, we're going to talk about how to deal with fatigue where you have a cyclic loading condition that can occur. I also have a extensive lecture in YouTube that covers low cycle fatigue, high cycle fatigue, and fracture. But this particular lecture is much more of a simplification of what we're going to discuss. In reality, fatigue can be predicted under cyclic loading conditions where the stress varies as a function of time in that manner. I think everybody has taken a paper clip, and if you took a paper clip and you start bending it back and forth, you know that it doesn't fail the first cycle, but you do know it fails in less than 10 cycles if you bend it very nicely. So fatigue cyclic loading condition will first initiate as a crack initiation point, then it will propagate, and then it will lead to failure. So those are the kind of steps. And I also have a whole lecture that shows you what the behavior looks in the cross section. And so I'm not going to cover that here. But the point I want to make is that fatigue cyclic loading conditions occur, those conditions occur when you have an oscillating stress field. And here, what I show is the oscillating stress field. What you see here is that the nomenclature in fatigue, where you define the minimum stress here, and that's your maximum stress there. And then you have this mean stress. And when I say mean stress, let me write it for you so we don't get confused about what that means. That's your mean or average stress. And then here, this term right here is considered, is called the alternating stress. Alternating stress of the material. Okay. The average stress can be defined as you see here. The mean stress equals the maximum here plus the minimum divided by 2. And the alternating stress is equal to the maximum minus the minimum divided by 2. And that gives you half of that amplitude there. In the case of complete reversal, what we mean with that is that it reaches a maximum value and it drops all the way down, and the amplitude of the minimum stress is equal to the maximum stress. So in essence, the mean or the average stress, this average stress here, average stress is equal to 0. And then the alternating stress in this case is just sigma max. So the alternating stress becomes the most important factor in determining the number of cycles to failure. But the mean stress can play a significant role. So, for example, and that should make a lot of sense to you. So, if I had cycles going like this, and this alternating stress here was the same as this situation here. So, this alternating stress is the same as that one. That height is the same as this height, say. But the mean stress was higher, as you see in this plot. So, the mean stress, instead of being here, is over here. This is going to fail faster. And there are ways to account for that. I'll give some examples. Now, a lot of the stress strain curves are derived for fatigue complete reversals. So you have in the number of complete reversals, and you have the stress state in this axis. You have the number of cycles to failure in this axis. And what you notice is that there's a point in time where the material reaches some asymptote here. So what that means is if I'm operating at an alternating stress that's over here, say, and I go over here, it looks like I never intersect the curve. So that means that if the alternating stress sigma A is less than sigma E, or the endurance limit, then you could have infinite life. And it turns out there's a lot of materials that do actually do that. But there are some materials that do not exhibit that. So it's important to understand that it's not always the case, but for a lot of materials, that is the case. There's a endurance limit at which if you're below the stress, alternating stress, you have a number of cycles that's infinite. And then you have the sigma f here. That sigma f depends on how these curves are built, but that sigma f can be either 0.9 times the sigma ultimate, or sometimes sigma f is taken as sigma, the yield of the material. So something to keep in mind there. And here, when I say sigma critical, what I'm saying there is that if I'm going to operate, say, 20,000 cycles, I just go here, set that to 20,000, come here, and then say, okay, that's the alternating stress I should be operating, so I can then survive those 20,000 cycles. Very important there, that point I want to make. And this curve here, the way that's derived is using testing that varies the number of cycles to failure. You know, you basically do a test, and you apply alternating stress as a function of time, and when you reach the number of cycles, the sample fails. Now, the sample don't typically fail with a very tight scatter like this, for example. Usually the scatter looks a lot more, it can look a lot more, let me use a different color. It can look a lot more dispersed. So there's a lot more scatter in the data than the blue color. So in reality, the stress strain curve can have significant amount of dispersion. And so it's typical for us that if we know the number of cycles to failure that's going to take to fail the sample, or the material or the structure, we take the number of cycles to failure and we divide that by 4, given the amplitude of stress. And we do that as an additional life factor to cover us for that dispersion that we see in the testing. We use a factor of 4 for low cycle fatigue, which is usually less than 10,000 cycles. And we use a factor of 10 on life factors for very large cycles to failure. So one more time to repeat again. So say I have an operation at 20 megapascals, and I go here and say, okay, well, where that is in my curve, and then I come down here and say, okay, well, that's about, say 60,000 cycles. That's usually high cycle fatigue. So what you will say then is that if n critical equals 60,000 cycles, then the number of allowed number of cycles will be n critical divided by 10. That's for high cycle fatigue. And then you could divide it by 4 if it's low cycle fatigue. But this is the number of cycles that you should allow in a particular design. In this case, it would be like 6,000 as an example. So that's to, again, to account for the fact that this is not just a straight line, but you have a lot of scatter and the data is dispersed through this curve. What you see here is the equation to calculate number of cycles to failure, just using the equation. Typically, we know where point E is, so that's the number of cycles that you plug in here. And critical is the one that you're interested in finding. And F is the number of cycles to failure in point A, which is the fatigue strength of the material. And then you have sigma critical, which is the one that you specify, your alternating stress, that goes here. And then the endurance strength, it goes here. So you have all these numbers. You can then calculate the number of cycles to failure using the equation you see right there. And I'll be using that in a few examples. What happens if you have a situation where you have a situation where you have a mean stress. So again, remember these equations here, this curve that you see here was intended when you have complete full reversal. So what I mean with that is that in the stress as a function of time does this back and forth, where this maximum value and minimum value is equal to each other in terms of amplitude. So your mean stress then is equal to 0. And so how do we deal with a situation where the mean stress is not 0? So we corrected using the modified Goodman criteria or the Soderberg criteria. And the way you will do that, you will calculate, you will first calculate sigma critical using this formula, for example. So sigma A is the amplitude, the alternating stress. For now, use Fs as 1 for what I'm explaining. Sigma M is the sigma mean stress, the new mean stress, and sigma ultimate is the ultimate of the material. So that's criteria 1. You can see very clearly that if the mean stress was 0 and had a full stress reversal, this will be 0. And so you just get exactly what we have for complete reversal. Once you know sigma critical here, the adjusted value, you can now come back here and use the same formula you had here, but now sigma critical is adjusted. You're now accounting for the fact that the sigma mean stress is different. You can see very clearly here too that if sigma mean is close to the ultimate of the material, then the denominator blows up and the sigma critical goes almost to infinity. Which means that this term will then lead to very, very low cycles of failure, maybe close to basically 1 cycle to failure or 0. Okay, and so another criteria people use is instead of using sigma ultimate here in the denominator, sigma yield is used. So this is a little bit more conservative than this one. So Soderberg is more conservative. Now I use this one a lot more in industry than I do the Soderberg. I do believe the modified Goodman does a really good job in matching out of test data. Everything I discussed here, everything I discussed there is when you have a single component of stress that's alternating. But how you deal with the fact that you could have multiple stress states alternating. And so in that case, we gotta really figure that out. So a lot of people use the von Mises type criteria. As you can see here, it looks very similar to that. The distortion energy equation. A lot of structures are subjected to axial torsion bending, right? So using something like this is more appropriate. The alternating stress goes here in each of these parts of the equation because each of the components of stress could be alternating in that way. And they could be alternating at different rates too. So for example, shear could go from 0 to 20 megapascals, but maybe this stress goes from say -5 to 20 or whatever it is. So you have to be you put the amplitude here, the alternating part here, and all of them could look different. And that'll give an equivalent alternating stress. And then you repeat the same thing for the mean stress. And for each of those components, you're not going to have the same value. They may have different values of mean stress. And at the end, you get this, you will equate it to this equivalent value here. You can write the same equation in principal stresses, but let's not get hung up on that. The equation above can be written the same in terms of principal stresses instead, which may be a little bit easier to handle. But at the end, what you will do is you will use these numbers now in all your previous calculations. So you will use that equivalent amplitude, alternating stress, equivalent mean stress, and then the sigma critical is now used in this equation again to get the number of cycles to failure. So again, a very simple process for multi-axial load condition. What I want to do next is to move to some examples.